Okay, so this is the result that we last saw, and it involves the solution to Diophantine equations. Equations of this type ax plus by equal to c, where a, b and c are integers and where a and b are not simultaneously 0. Now we have already seen, in fact we have proved that this equation has a solution if and only if d divides c, where d is the greatest common divisor of a and b. And by solution, of course, we mean integers x and y, not just real numbers. Okay. So this part has already been proved, but there is this second part also, which tells us exactly what all the solutions are. So if the integers x0 and y0, whatever they are, they constitute one solution, any particular solution to this equation, then all the solutions look like this, where t is an arbitrary integer. That is, you vary t over the set of integers, you get the solutions. So now we need to prove this second part. And just like the first part, which is an if and only if statement, in the second part also we need to prove two things. The first thing is that these pairs of integers, these x and y, these kind of pairs, all of them are solutions to our equation. And the second thing we need to prove is that any solution in fact is already here among these solutions. So let's see the proof now. Okay, so in the beginning itself, we are going to use this fact that x0 and y0 constitute a particular solution, since this is a solution to ax plus by equal to c. So you can use them in the equation and the equation will be satisfied. So ax0 plus by0 is equal to c. Now let us first show the easier half, that is that these expressions form a solution. Now, and these expressions all form a solution means that regardless of what the integer t is, in fact you will get a solution. So for any integer t, we have, so we are just directly going to substitute these expressions in our equation. x0 plus b divided by t times t plus b times y0 minus a divided by t times t. From this we get ax0 plus by0. We keep them together obviously because of this, and besides them we also have ab divided by d times t minus ba, which is also the same as ab divided by d times t. So they cancel out and this gives us c. So yes, all of them are actually solutions. Next, conversely, let x prime comma y prime be any solution to our equation. That is, have I already lost ink? Just give me a moment. So now we have ax prime plus by prime equal to c. So we can now use these two equations together. Hence, ax prime plus by prime is equal to ax naught plus by naught. And this implies, after rearranging terms, we would get something like this. A times x prime minus x naught is equal to b times y naught minus y prime. Obviously. Now, by there was a result, if you recall, that if a and b are two integers, just like how we have them here, not both of which are 0, and d is their GCD, then the GCD of a divided by d and b divided by d, which both of which of course are also integers, is 1. Another way of expressing this fact is to say that if you take apart the greatest common divisor of a and b, whatever that is, whatever are left, those integers would be relatively prime. That is, there won't be anything else left other than 1, other than the common factor 1. So we are now going to use this result. And the result, the exact thing is Theorem 2.4 by Theorem 2.4. There exist relatively prime integers r and s such that a is equal to dr and b is equal to ds. So this r is of course that a divided by d and s is b divided by d, and their GCD is 1. Thus, now if you use these expressions here in this last equation above, then you get this dr times x prime minus x naught, that is equal to ds times y naught minus y prime, which would imply, I mean, we are now able to cancel d from both sides. But in any such cancellation, you of course should first of all make sure that the thing you are cancelling is non-zero. D is non-zero because it's the GCD of a and b, and it's by definition a positive integer and hence non-zero. So we can just simply write r times x naught minus, x prime minus x naught. Things will be wrong if we forget this order. That is equal to s times y naught minus y prime. And this implies what? This implies that the right hand side is divisible by r because the right hand side is an integer multiple of r. X prime minus x naught is an integer. So this implies that r divides s times y naught minus y prime. Okay. Now since r and s are relatively prime, that is, since their greatest common divisor is 1, so we can apply Euclid's lemma here. Euclid's lemma then gives us this fact that r would then have to divide y naught minus y prime. So y naught minus y prime is an integer multiple of r, where t is some integer. Now from this we are in fact actually we have got the desired expression for y prime. Hence y prime is y naught minus rt, which is equal to y naught minus r is a divided by d times t. Okay. Now before we get the other thing, that is the required expression for x prime, you note that in the original Diophantine equation we still have that condition that both a and b are not simultaneously 0. So even when one of them is 0, the other must be non-zero. So that means in any case at least one non-zero coefficient is there. Now what I am going to additionally assume is that in fact that non-zero coefficient is a without losing any generality. Why? Say the non-zero coefficient is not a. Say your equation is this, where b is non-zero. Fine, then no problem. You just simply write your equation like this. But you would say that no, we are actually losing generality because this is not x, this is y, and this is x. They are different variables. Of course, they are different variables, different but related by this equation. But the fact is that it does not really matter which one you call x and which one you call y. These are just simply names. Okay. So just like you can consider any coefficient to be the one appearing with the first variable, you can in fact make any one of these two variables the first variable. So I am going to now assume without loss of generality that in fact a is non-zero. Actually I should have written it beforehand, but I forgot. It does not really matter. It does not create any logical problem. We can assume it now also. So far we have not needed it, but now we are going to need it. Since a comma b are not both 0, we can assume without loss of generality that a is not equal to 0. Now what does this imply? What is it, the consequence of this assumption? This implies that r is not equal to 0. Okay. Now look at this equation. Y naught minus y prime is rt, so we can just simply use it here. Now r times x prime minus x naught is equal to, in place of y naught minus y prime, we are now going to write rt, so srt. And now, due to the non-zero nature of r, we can cancel it from both sides. So this implies x prime minus x naught is equal to rt. And now, of course, you can see we are going to have the expression for x prime. So x prime is equal to x naught plus rt. Oh, sorry. See, I said I cancelled r and I am again writing r. This is st. So b is ds, that means s is b divided by d. So that's how we have been able to prove that any solution consisting of two integers x prime and y prime already appears there in that list. Okay, it has already been accounted for there. So we are not losing any solution, we have the full list of all solutions, and here the proof ends. And let us now see one example illustrating this whole thing. Consider the Diophantine equation. So this is the equation 172x plus 20y is equal to 1000. So to know whether this has a solution or not, we of course have to calculate the GCD of 172 and 20. Here both are non-zero, because if one of them is 0, actually the situation is quite trivial. In that case, say in place of 172 we had say 0, that means 20y is equal to 1000. Then also by that same result, what would be the GCD in that case? GCD of 0 and 20 is 20. So you would then have to see whether 20 divides 1000 or not. It in fact divides. But in this case also we will see that division is there. So there would be a solution. We now calculate this. By the Euclidean algorithm. Why Euclidean algorithm? Why not by any other means? That is because the Euclidean algorithm not only allows us to calculate the GCD, but it also allows us to express the GCD as a linear combination of these two numbers, which would in fact tell us, which would in fact give us a particular solution. And then based on that solution, we would write down the other ones using the second part of our theorem. So we now have these equations, which of course you would, what you have to do repeated divisions in a specific manner. So these are the results of that. So at each step we divide the divisor by the remainder, and in the first step of course we divide one of the numbers by the other one. Which one, that is up to you, until we get a zero remainder, which is bound to happen at some point. So the first non-zero remainder, I should not say first non-zero remainder because we are starting it from here, no, last non-zero remainder, 4 is the GCD. So by the Euclidean algorithm, this is equal to 4. Now 4 actually in fact divides this, since four divides 1000, the given equation has a, if I simply write equation has a solution that has a slightly different meaning, but I should mention Diophantine. A Diophantine equation having a solution means the solution is an integral one. Okay, let us now express the GCD as a linear combination of 172 and 20. Okay, how can we get that? By working backwards, starting from here. So this equation gives us what? 4 is equal to 12 minus 8. Then what you do, you write an expression for 8 from the previous one. So 8 is 20 minus 12. So that gives you what? 2 times 12 minus 20. And then you write an expression for 12 from this previous equation. 2 times 172 minus 8 times 20 minus 20, that is 2 times 172 minus 8, so this is minus 16 and another minus 1, minus 17 times 20. Hence 1000 is equal to 250 times 4. But let me just yes, I should be very careful because I am extremely bad at this type of calculations, which is something you already perhaps know. I can argue logically, but actual arithmetic the actual process of manipulating numbers and the familiar operations, addition and multiplication, that I am very bad at. Worse than what perhaps you would be able to do. Okay, so here what are we getting finally? 500, yeah, this is 500. 500 times 172 plus, and then this would be what, how much? 4250 times 20. Let me just quickly verify it. Yes. Okay, so this expression, I mean this final equation gives us a particular solution, and that particular solution is x equal to 500 and y equal to minus 4250. And from this particular solution we will be able to write down all the solutions. So we just conclude that. So x equal to, in fact, because this is a particular solution, let's just maintain the notation we used in the actual theorem. So x naught is 500 and y naught is minus 4250 is a particular solution to the given Diophantine equation. Thus, all the solutions are x equal to x naught plus, it's first better to write the actual form of the solution, and then of course you can put your special values. So what is our x naught? Our x naught is this, minimizes the chance of making error. And what is our b? B is 20 divided by 4 is 5. So that means 500 plus 5t. And y is equal to minus 4250 minus 172 divided by 4, which gives us what? 43t, where t belongs to the set of integers. Now one may of course be interested in still a further restriction where one wants positive solution where both x and y are positive integers. Note that in this particular solution x naught is positive but y naught is negative. So we are now going to see if that is possible, whether there is in fact a positive solution where both x and y are positive. For a positive solution, we must have we have the general expression, so let's just see what they give us. 500 plus 5t should be greater than 0, and at the same time minus 4250 minus 43t should also be greater than 0. And these two inequalities imply what? The first one implies that 5t, or if we go one step further, t should be greater than minus 500 divided by 5. Okay, still greater, because after all we are dividing by 5, which is positive. So minus 100. And what does this one give us? Minus 4250 divided by 43 is greater than t, or okay, I'm just being a little sloppy here. Okay, you understand that this I am doing only for this inequality. Now if one actually calculates, it turns out that this value is roughly what? Minus 98.8372, something like this. So in order to have a positive solution, this integer t should be, keep in mind t is an integer, so that integer should be strictly less than minus 98. In fact, it should be less than this number, but at the same time it should be greater than minus 100. So there is in fact one possibility, and only one possibility for t, namely that t should be equal to minus 99. So we must have t equal to minus 99. The solution corresponding to this value of t is, one can calculate using the expressions for x and y that we found out, that in this case x would be 5 and y would be 7, I think. Yes. So you see that we have found not just a positive solution, but where the values are in fact much smaller than the original particular solution that we found, where x is 500 and y is minus 4250. So here this example ends, and it also shows us how to go through the process. If we have a Diophantine equation, then first we check whether it's solvable or not. If it is solvable, then how to find all the solutions. And if we additionally put some more, a little more effort, then we can in fact get a much more manageable solution than the original one, which is given by the Euclidean algorithm process, where we work backwards and express the GCD as a linear combination. That process gives us, it will give us some solution if a solution exists, but a nicer solution may also exist somewhere else. If we, in fact, this is not the only way to find a nicer solution. You just use the general expressions for x and y. There you just put some values of t. Say if you put t equal to 0, you are going to get that particular solution which is given by your Euclidean algorithm. But you put some other values of t and see if things can be made much easier, much nicer, like what we have here. So with this I end this video. If you want to make a comment, you can use the comment section below, or you can mail me. My address will be there in the description. The link will be given. And the next video is on Friday, of course. And on Friday, let's go back to field theory again. So with that, I just wrap things up. So see you on Friday with field theory. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice night.